Okay, a second one. How many of you are familiar with MLIR compiler infrastructure? Okay, yeah, much more. Okay, let's get started. So today's topic are divided into 4 partitions. So the motivation. So firstly, so we are in the software 2.0 era. So lots of software are now trained AI models. So in the software 2.0 era, so NVIDIA CUDA dominates more than 90% of the market share for training and inference. And here are lots of ML frameworks, such as Pytorch, Tensorflow, JAX, ONNX, etc. And lots of AI startup companies are building accelerators with different architectures. And all they are writing low-level kernels with different programming language, with different runtime APIs. Okay. So RISC-V, so now we have some RISC-V companies. They are building AI accelerators with RISC-V scanner and RVV and IMX or AMS extension, etc. So the problem is, so each AI accelerator vendor build ML compilers and target specific kernels for their own. So just like the diagram on the right, so we are expecting to have a unified ML compiler to bridge the gap between the AI framework and the various accelerators. But the reality is, on the bottom side of the diagram, so we have built lots of adapters to bridge Pytorch into NVIDIA. Yeah, that's the reality. So our solution, so there are already some Triton kernels in Pytorch, and we are also writing some Triton kernels for CMD architecture and non-CMD architecture. Why should I mention CMD and non-CMD? It is because the memory hierarchy abstraction in these 2 different kind of architecture are different. So even Triton programming language is target independent, but we have to write different kernels for different memory architecture for optimal performance. That's why we have to write different kernels for different architecture. So we have Triton language for our kernel solution, and we are providing Aries, which is an MLIR-based ML compiler, and to bridge the gap. So we use the model importer from Aries to import ONNX, Pytorch, and the TensorFlow model into unified MLIR. And we compile Triton language and the computer graph of ML model into a unified ML dialect. And based on that, we can do a more aggressive compiler optimization, such as kernel fusion and kernel computer graph fusion in a single compiler dialects. So, okay. So Triton for RISC-V. Here is a quick look of a GEMV kernel in Triton. So there are a few highlights in Triton programming language. The first line in the GEMV kernel is TL program ID. So the program ID gets the dimension from X, Y, or Z dimension for given problem. So here, the program ID gets So its parameter is 0, though. So it gets the problem space from the x dimension. And we have seen there are some TL-started function call. So for example, in the call loop, there are two TL.nodes. It's a kind of overloaded function. So the function is overloaded based on the parameter of it. So if the parameter is a vector, the function loads a vector of stuff into its target register. If the parameter is a high-dimensional tensor, it loads the high-dimensional data into targets. So the language is highly overloaded. So this is a quick go-through of the Triton programming language. Okay, so there are some highlights of Triton programming language. So it's open source GPU programming language for neural nets from OpenAI. So it was initially designed to program GPU. Okay, it's a Pythonic language. And the performance of that language is on par with CUDA on CUDA GPU. And it supports JIT and ahead-of-time combination. And the main difference of Triton with other programming language is that Triton is a block-level programming language. So while OpenCLC and CUDA C++ is a kind of SIMT programming language. So OpenCLC and CUDA C++ program for a single thread. And C++ program for the whole workload. But the Triton, so it program for a tiled loop. So you explicitly program for the tiled loop and let the compiler to choose the best mapping between a whole workload into the tile. So that's the main difference between Triton and the other programming languages. Okay, so for programming language, there should be some compilers. So there are three, in my best knowledge, there are three compilers. The first one is the official OpenAI Triton compiler. It mainly targets NVIDIA GPU. So it's also a MLIR-based compiler. And the second one is Triton CPU. It was initialized by Intel and Meta. So it is mainly targets x86 SIMD instructions. So in the compilation flow for Triton CPU, it lowers Triton IR directly into MLIR vector dialect. So the vector dialect will directly lower into LLVM SIMD code to x86 intrinsic functions. So for Triton CPU, the cons, it lacks of high-level dialect support. So it's kind of, I think, x86 specific compiler. And the third compiler is Triton Shared. It was initialized by Microsoft. It targets CPU backend initially. So Triton Shared is more generic than Triton CPU, as it lowers Triton IR into MLIR lineage dialect. The lineage dialect is a kind of target neutral, and it is designed to do linear algebra transformation kind of optimizations. But the performance of Triton Shared is not as promising as Triton CPU currently. Yeah. So those are the three compilers I have investigated. Okay. So why Triton for RISC-V? So because Triton is a target-independent programming language. So it's designed to program ML kernels. And most of ML kernels are written in Triton in Pytorch 2.0. I think there are more than 100 kernels already written in Triton language. And the proven performance on GPU give us expectation to try that on RISC-V CPU. And from our experiment, we saw promising performance from Triton CPU for RISC-V. Okay. We're not using CUDA, C++, OpenCLC, as I just mentioned. It left too much low-level programming language features to the end user. I think we should, as a compiler guy, we should abstract away non-performance critical or compiler durable feature into the compiler, so we can let the community to write a target independent kernel more easily. I think this is is an important reason. That's why we didn't choose OpenCLC or CUDA C++. Okay. Next one. Okay. Here is the example of Triton programming language, CUDA and C. So I will I will just talk about the difference, the important difference between Triton language and the CUDA. So for Triton language, we have to explicitly specify the workload dimension and the tiled workload for the kernel. And for CUDA, you can see we only program for a single thread. We use thread index .xyz to get the thread ID of that kernel runs on. And for C and C++, the whole workload is expressed in the for loop. So the compiler will do all the optimization work for the C kernel. So that's the main difference between these three kinds of different programming languages. Okay, for the benchmark, we have done lots of benchmarks. So the target is space MITK1. It's RVA22 profile with 256-bit RVA 1.0. So we have written C and Triton kernels for large language model and computer vision. So we have tested those kernels with different shapes, but with aligned algorithm to compare apple to apple, not apple to orange. So for the combination flag, we all use -O3 to achieve the best performance for the compilers we have used. So for C kernels, we have benchmarked it with GCC 15 with auto-vectorization. And we also have benchmarked C kernel with ZCC 3.4 with auto-vectorization. By the way, ZCC is LLVM-based optimized compiler with enhanced auto-vectorization. And for Triton kernel, we have benchmarked it with ZCC 3.2.4 with auto-vectorization. And for all these benchmarks, we run them in 1, 4, and 8 multi-threading. And the best of all the kernels in C and Triton and all the script for running those benchmarks are available on the GitHub link at the right side below. Okay, for the rotation position in binding kernel. So there are 3 groups of data. So on the chart from the right side of the screen, so the orange and the blue and the green lines are the single-threaded performance for the 3 kernels. And the green line in the middle is not obvious, but the green line in the middle are 4-threaded performance. and on the top, they are 8-threaded performance. And we can see from the table and from the chart, Triton has similar performance against the C kernels. But because the Triton compiler generates fixed vector length, so the masked node generated from Triton kernel, not variable vector generated for that. And so the multi-threaded Triton kernel outperforms RISC-V GCC by roughly 15 to 18%. So the highlighted the red number in the table. So and we have seen the bottleneck of multi-threading for more than 4 kernels. I think this is due to the memory bandwidth of that platform. Okay, for MatMore, I think this is the workload which takes more than 90% of the computation time. So we run matrix MatMore in 16 by 16. So the Triton kernel outperforms C kernel by a big win. We can see there are more than 15 to 40% improvements against C kernels on various C compilers. And then the performance scales linearly for multi-threading for Triton kernel. So, and we also analyzed the performance issue on this compiler. So if we tile the kernel with 32 by 32, the Triton kernel will have the same performance as C kernel on this compiler. Okay, so and the performance for GCC compiler is not as good as others because GCC generated threaded node. Okay, and we can see there are some shapes from the graph. There are some performance is very bad for particular shapes. We are still analyzing the performance issue for that. Okay, this is the performance for softmax. We can say Triton kernel has on par performance for as well as C kernels. For RISC-V vector extensions, Triton and GCC generates VFmax and F reduction sum. But GCC compiler only generates Fmax with loop on road. So the performance is roughly the same, but and the performance scales for multi-threading program. But we can see from the chart, as the shape goes up, the performance of eight threads drops. It is because the memory bandwidth limits this algorithm. Okay, for layer normalization, so we can see Triton kernel outperforms GCC in single-threaded mode by 13%, but GCC is 7% better than Triton kernel. So for multi-threading, Triton kernel is not as good as the C kernel. So we are still trying to identify what's the problem of the Triton programming language. So our initial thought is Triton kernels use fixed vector, not using the scalable vector. So I think there are some overhead to compute the mask memory node. So I think that's one of the reasons why it doesn't work well. Okay. For resize, it's a computer vision kernel. So we can see Triton kernels has on par performance against the ZCC, and both Triton and the ZCC is almost 3 times faster than GCC. So why GCC performs bad? Here are the reasons. So GCC generates threaded memory nodes with permutation instruction. So we all know permutation instruction may perform bad on some vector architecture. And the threaded memory node is not optimized because you can't optimize threaded memory node or index memory node on AXI bus. And the Triton and ZCC generate index node, but without permutation instruction. So index node is also as bad as threaded node, but there is no permutation in Triton and ZCC. Okay. And for multi-threading, we can see only Triton and ZCC scales linearly, but for GCC, the performance of the multi-threaded version is very bad. Okay. Okay, warp is a kind of image transformation algorithm. Okay, so the Triton kernel outperforms ZCC by roughly 9 to 20%, and it outperforms GCC by roughly 50 to 100%. So here's the reason. So Triton and the ZCC compiler uses a larger register group. It uses MA and E64. But GCC here in this benchmark uses E64 and M1 grouping. Okay, we have tried to manually change the GCC to use Elmore to M8, and it improves GCC performance by 100%. Okay, and we can see the Triton kernel performs better than ZCC in that so ZCC generates no index node instead of unit threaded node in Triton. So for AXI bus, we can optimize unit threaded node as a burst node. Okay. The last one. So the Triton kernel only outperforms ZCC in A thread by 20%. So it is on par with ZCC for single and four threaded benchmarks. And GCC has overall 10% performance gain than Triton kernel. So we have tried to identify the reason. So we have tried to change the register grouping for ZCC. So we can see there are 15% improving by changing the ZCC grouping from M4 to MF4. This is interesting because in the previous kernel, we have boosted the performance of GCC by changing the register grouping from M1 to M8. But here, the performance is becomes better when we're changing the register group from a bigger one to a smaller one. So we still don't know what the reason is. We are still trying to find out the reason. So for the instructions, Triton kernel generates separate instructions for multiply and add. But for the C kernel version, we have generated a fused instruction VM Mac. Okay. Okay, so the summary of those 7 kernels. So in general, we have seen Triton kernel has on par performance against C kernels. And it can be auto-vectorized by GCC and ZCC for RISC-V targets. And it can be parallelized by OpenMP with MLIR OpenMP dialects. So the combination path of the Triton kernel goes through from MLIR to LLVM. So we use Triton CPU compiler as compiler front end, and the ZCC compiler as backend compiler. So just as I mentioned before, so the memory bandwidth limits the multi-threaded kernel performance. So what we are going to do in the future? So we are going to write a compiler for Triton on MLIR, which will follow Triton shared style. So we are going to lower Triton programming language into MLIR called dialects, and we'll try to optimize Triton kernels with computer graphs together. So it will expose more optimization opportunity against the traditional ML compilers. Okay, talking about MLIR, here is the complex code gen path for MLIR. I only highlight a few of the paths. I think it's too small to see the words on that. Okay, so I don't know if you guys can see the words or not. So actually, in MLIR, there are a few core dialects. There are lineage, tensor, math, affine, vector, memory ref, SCF. So basically, if we want to try to optimize a common compiler problem, if we want to try to optimize Triton programming language with ML computer graph, we are going to do the optimization on lineage and affine and SCF on those core dialects. And once we have done the optimization, we can lower all those core dialects into LLVM, which will go through into LLVM compiler backend to do the code generation. Okay, here is not maybe a new term. So we call this compiler a big compiler. So compared to traditional compilers such as GCC or LLVM, so what is a big compiler? So big compiler compiles languages and computer graphs into a heterogeneous platform. And it also abstracts runtime API and hosts device communication within the compiler. So the kernel programmer will benefit from this because they are no longer write kernels with runtime API. So that's fundamental to provide target independent kernel libraries to all the community. Okay, and our compiler is also based on Aries. Okay, so introduction to Aries. So Aries was initiated by Google, but now I think it is maintained by AMD. Yeah, so it is an end-to-end compiler stack for ML model. So it has ML model importer to import Pytorch ONNX JAX model. And it shares the same core dialects as MLIR, such as lineage, affine, Aries. And Aries also defines a few core dialects to do computer graph optimizations. So the first one is flow. Flow is a target-independent graph description dialect. And there are lots of graph partition and optimization algorithm in Aries, which is based on the flow dialects. And once we have done the graph partition on flow, we are going to map the partitioned subgraph onto real hardware. So we use stream dialects. So there are some target-related constraint built into stream dialect. And And those target-related constraint was introduced by hardware abstraction layer dialects. So this compiler, so it has target awareness algorithm in the compiler framework, but the algorithm is target independent. So all the target dependent parameters are built into a compiler options or config file. So we write target independent algorithm to do the graph partition. And so each target backend will provide a description to describe the computational power, the memory hierarchy, and this memory hierarchy for your target. So you don't need to modify the whole framework to adapt new hardware. Okay, so our big compiler, Magic, is based on Aries, but it is beyond Aries. So for the AI application, we are going to support Mojo and Triton programming language in our compiler. But Mojo is not open source yet, so we will support Triton first. We are going to lower Triton IR into MLIR core dialects and merge Triton IR core dialects with computer graph dialects and do inter-procedural optimization on the core dialects and lower it to target specific dialects. Also, you can see there are two different applications on the left side and the right side. The left side is a software path. The right side is hardware path. While we were doing the big compiler, we have found out actually we can also do the same optimization for C, C++, Fortran, and Rust. So currently, we are upstreaming clone IR support to support C programming language feature to lower that into the common MLIR infrastructure. And we are going to do the same kind of graph partition for C programming language. Yeah. Because we have found out some data flow architecture, such as the RISC-V and wormhole AI chip from Tensorflow, is a kind of HPC architecture, and we can compile some kind of HPC application directly onto that data flow architecture. By using MLIR, it is more easy to do the graph partitions than traditional LLVM backend. Okay. Here are the few highlights I just mentioned. Okay. Okay. So we are going to contribute open source Triton kernel libraries to upstream, to Pytorch and some third-party library providers. And we are going to have a Triton compiler and a unified ML compiler to solve the complexity of nodes of AI frameworks and the nodes of AI accelerators, and bring that into reality. Yeah, thank you.